Okay, so today we were happy to have Gian, Giudice from CERN to tell us about self-organized localization, solution to all hierarchy problems. Please, Gian.
Thank you very much, Victor. Thank you for the kind invitation. It's really a pleasure for me to speak at Stanford. So in spite of the physical distance, I think that I'm really with you with my spirit and my heart. So, oh shoot, I have a problem changing the slides. I should have checked with that before. I think I have to go out, sorry. Let me try again.
Okay, no problem.
I think I have to open after I. No, this is still a problem. No, that doesn't work. Okay. Now you can see it, right? So the symmetry paradigm is the successful principle that defines our understanding of nature in terms of general relativity and the standard model. It's a big mess here, but okay. So in imposing a gauge symmetry is an elegant and constraining requirement that identifies a theory and leads to sharp predictions. And gauge symmetry has been the triumph of particle physics. So it's not surprising that symmetry has been the starting point to attack problems beyond the standard model. The cosmological constant, Higgs naturalness, the flavor structure. However, in these contexts, at least so far, the success has been less striking. Many new fascinating concepts have been introduced, like technicolor, supersymmetry, extra dimension, compositeness, but it's still unclear if any of these provide the right answers to those questions. It is then natural to look for new directions, and there is a lot of ongoing effort in trying to identify new paradigms, especially in the direction of linking some of these problems to the early history of the universe. And this seems to me a fruitful research direction. So today, I'd like to present one of these attempts, which goes under the name of self-organized localization, and was proposed together with Matthew McCulloch and Tae-Wong Yu. The basic concept is that the fundamental role as organizing principle is not symmetry, but criticality. I should remark that a similar point of view was expressed in a series of very interesting papers by Justin Curry and collaborators. Their approach is different from ours, but the interesting common aspect is that their approach and ours highlight the effectiveness of the language of quantum statistical mechanics in the context of eternal inflation. So critical phenomena have always played a central role in physics since the time of Ehrenfest and Landau. And also phase transitions are known to play a fundamental role in the history of the universe. Take the QCD or the electroweak phase transitions. And phase transitions may be the cause behind phenomena like inflation or baryogenesis. These are classical phase transitions. So in a classical phase transition, the phase of the theory changes as the temperature is varied. Take the familiar case of the ferromagnet. When you lower the temperature below the Curie temperature, order spontaneously emerges in the form of a bulk magnetization. Classical phase transitions are familiar ingredients of cosmology, but here I want to consider quantum phase transition. In a quantum phase transition, it is not the temperature that varies, but some external field, for instance, a magnetic field. Let me make a simple example. Take a microscopic theory in which you have an operator O coupled to an external field phi. The VEV of O is 0, but below a critical value phi c, similar to the case of the ferromagnet if you want, the theory makes a phase transition and O develops a VEV. As a result of the sudden phase transition, the first derivative of the potential V of phi has a discontinuity at the critical point. In other words, the first order phase transition of the microscopic theory makes the phi potential non-trivial at the critical point. So our goal is to use quantum phase transitions as triggers to determine physical parameters. The idea is based on two essential ingredients. The first is that some parameters of the microscopic theory, and by microscopic theory, I mean the standard model or any of its BSM extensions, you'll see examples, are promoted to functions of one or more scalar fields. So during inflation, this scalar field is light with respect to the Hubble rate, and therefore its background value varies stochastically as a result of quantum fluctuations in the Sitte space. And as the scalar field random walks in its field domain, the standard model parameters change in different parts of the universe and at different instants of the cosmological history. So effectively, this means that there is a multiverse where standard model parameters take all possible values in different space-time patches of the universe. This is by now a rather familiar picture in physics. Actually, it is similar to the case of the axion, in which a standard model parameter, theta QCD, is promoted to be a function of a light scalar field, the axion, and therefore undergoes a random walk during the inflationary phase. It is also similar to many attempts where the cosmological constant is promoted to a dynamical variable. Think of going back to the pioneering work of Abbott, O'Brien, and Teitelbaum. The second ingredient concerns the selection mechanism. In other words, how a particular value of the standard model parameter is selected out of all possible values that can be realized in the multiverse. So different selection criteria have been considered in the past. For instance, in the case that I was showing before of theta QCD is selected in the solution of the axion is selected by a symmetry criterion. Because the scalar potential is minimized, the scalar potential of the axion is minimized at a point at which CP is conserved. Weinberg proposed an anthropic criterion as a way of selecting the cosmological constant. The relaxion uses a back reaction from electroweak braking. There are many other dynamical selection mechanisms in the literature. What we propose is that criticality is a selection mechanism. So criticality and not symmetry may be the secret for understanding the values of some of the parameters of low energy theory. So the universe dynamically prefers to be at the verge of a phase transition, in a metastable phase, ready to collapse to a different phase. And the low energy parameters are dynamically selected to place the universe at this critical point, even if these values do not correspond to a point of enhanced symmetry. So let's see how self-organized criticality operates. So the language that I've chosen to use is the one of the stochastic approach introduced by Vilenke, Straubinski, Linde, and many others after. The central variable is a distribution P of phi and T that describes the volume occupied by the field with a certain value phi at a given time T. in an expanding universe with Hubble rate h. So the dynamical equation is the volume-weighted Fokker-Planck equation, which I will call it FPV for short. The time evolution of P is determined by 3 terms. So this is the classical term that describes the tendency of the field to reduce its potential energy as a result of the classical force proportional to V prime, the derivative of V with respect to the field. This term describes the quantum effect. So in the language of statistical mechanics, it is the diffusion term that broadens the distribution as a result of thermal fluctuations in that case. In our language, it is a pure quantum effect. And then the third term describes the expansion of the physical 3D volume in de Sitter space. So it is interesting that dimensional analysis shows that these 3 terms correspond respectively to classical physics, because that term persists in the limit h bar to 0 and m Planck to infinity. The second term is determined by quantum physics, because it vanishes in the limit h bar to 0. And the third, gravitation, because it vanishes in the limit m Planck to infinity. So SOL, self-organized localization, is really an effect of these 3 pillars of physics: classical mechanics, quantum mechanics, general relativity, coming together in the description of critical phenomena. So the physical language of the FPV can be traced back to the known result that the Fokker-Planck equation gives the average over a large number of random walks described by the Langevin equation. Remind you that the solution of the Langevin equation gives a single trajectory of the field subjected to the classical force, proportional to V prime, and to a Gaussian random noise, proportional to the Hubble rate, which describes the physical effect that randomizes the trajectory. Now, why doesn't it work? I can't exchange again. Sorry, let me stop sharing. I don't understand what's going on. Let me try to share the full thing to see if now this works better. No, it doesn't change the slide. Ah, here we go. Now it does. Sorry about that. Okay, so I was explaining the terms, and the additional volume term in the FPV means that when taking the average, we weigh each of the trajectory with a volume factor e to the 3ht, which describes the expansion of the physical 3D space. And because of this additional factor, P loses the meaning of a probability distribution. The solution of the usual Fokker-Planck equation is a probability, because it describes a probability distribution of the Langevin trajectories. And indeed, it has a conserved current, because the time derivative is equal to a total field derivative. In the FPV, this is no longer true, because the weighing with the volume factor spoils current conservation. Therefore, the solution of the FPV is not a probability, but a volume distribution, whose normalization doesn't remain constant with time, because the total volume keeps on expanding. And we will use this, this distribution P, that is a solution of the FPV equation, as our measuring tool to make probabilistic prediction in the multiverse. Now, this is a strong and even controversial statement. So before I continue and give you examples of SOL, let me open a parenthesis and discuss several open problems related to this statement. So the first is the gauge dependence of our parameterization, or in other words, the dependence on the choice of time foliation. To test the gauge dependence of our result, we redefine the time coordinate according to this law, where h is a field-dependent Hubble rate, and h naught is a reference value, and we choose it to be a characteristic of average value of the expansion rate. And psi is a number that varies between 0 and 1. Obviously, this is not the most general coordinate reparameterization, but it describes a family of gauges. And it is a representative family because as I vary the parameter psi between 0 and 1, I interpolate between two interesting cases. When I take psi equal to 1, I get what is called proper time. And when I take psi equal to 0, I get what is known as the E-folding gauge, which corresponds to a time coordinate which measures the number of E-foldings accrued by each patch. So in this special gauge, the volume term becomes exactly field independent. Therefore, it simply amounts to an overall time-dependent rescaling of the solution. But the field value has no impact on the volume weighing procedure. Since for us, the field dependence of the distribution P is central for the selection criterion of the multiverse, this case is the most pessimistic choice. What we find, and I'll show you the result, is that the localization of P at the critical point is a gauge independent result. However, the degree of localization, which is measured by the width of the distribution P peaked at the critical point, is instead gauge dependent, with the distribution getting broader as psi goes to 0, because as psi goes to 0, you lose everything. So in all practical application, the distribution is parametrically so sharply peaked that localization is lost really if you go exactly xi equal to 0 with astronomical accuracy. Of course, this is not satisfactory, that the result have a remaining gauge dependence. But the way I view this result is that it's an indication for an underlying physical phenomenon. Waiting for a better description. So a second different but not unrelated open issue is a well-known measure problem. To make a probabilistic interpretation, we have to define the statistical ensemble in the multiverse to compare probabilities for the outcome of any single universe. Now, a meaningful way to do it is to compare universes at their corresponding reheating times. This is because reheating is a moment at which observable universes are born. So since we are interested in the probabilistic distribution of standard model parameters, at the time inflation ends, we should compute the distribution of the field phi on the reheating surface. I remind you that the reheating surface is the three volume hypersurface of all the reheating events in space-time. So, however, the reheating surface can be computed only once the inflationary model is specified, and we don't know the right model of inflation. Moreover, there's a bigger problem, which comes when you consider eternal inflation. So I will show in the following, in all applications that I will show, SOL requires eternal inflation. And in eternal inflation, new universes are continuously created. And the reheating surface is infinite and non-compact. The nature of the reheating surface in eternal inflation makes any probabilistic interpretation difficult, not only in practice because we don't know the model of inflation, but also in principle, because any relative probability is infinity divided by infinity. And this is the measure problem. Now, there's been several ways to have been proposed in the literature to deal with this problem, and all the best cosmologists have attempted to attack this problem and to, in order to regularize infinities with various procedures. I think it is fair to say that none of them can be regarded as a successful final answer. So in our context, we use the fact that the FPV equation admits steady state solutions. In other words, the phi distribution after a sufficient time reaches a form which changes with time, but only by an overall factor. And the functional dependence of phi remains constant and has a universal asymptotic behavior at large times. So although we cannot compute the overlap between these steady state distributions and the reheating surface, their property of remaining identical in time is indicative of the fact that they could carry some physical information. So in this sense, we have conjectured that critical points are attractors during inflation. And our calculation, I think, could be taken as supporting evidence, but absolutely not as a final proof. No final proof can be given until the inflationary model is known and the measure problem is solved. It is well known that assigning a probabilistic interpretation to steady state distributions for the inflaton leads to a problem if we use a proper time gauge. And this problem is called the Youngness paradox. Now, I had a slide to explain it, but I think all of you, I think, are familiar with that. So let me skip the explanation. But essentially, the problem boils down that the new vacua are created, and the ratio of new to old vacua grows exponentially with time. So this means that there is an exponential preference always for newly created vacua. And in turn, this means that there is an exponential preference for our universe to be as young as possible, and therefore the CMB temperature to be as close as possible to the maximum temperature, say to the reheat temperature. In other words, our universe is exponentially unlikely. And this may suggest that our use of proper time steady state for the field phi is incorrect. However, I want to argue that this is not true, because it's very easy to see with constructing examples like the one that I was showing before, that well, first of all, the phi field in itself does not introduce a Youngness paradox because it's only a small perturbation. And it's also easy to construct models in which even if you impose the same measure, and this is done, for instance, with a measure proposed by Linden, the same measure for both the inflaton and phi, the two probability distributions are independent because the two fields evolve in a independent way. So in conclusion, just to make this story short, given that I don't have a definitive answer, I would say that it's impossible to make firm statements about the result without knowing the model of inflation and the ultimate solution to the measure problem. However, our results are consistent, and they could be viewed as indicative that Sol is a general physical phenomenon existing in eternal inflation. I think from the examples you see what is the physical content. Of course, there is a lot of work that has to be done, but I hope that these our paper on Sol may actually further motivate research in this direction. Why doesn't it change? Damn I don't understand. It is just. I don't know. It's a complete mystery to me why it doesn't change. Anyway, I was listing the problems, and the list is long, is not finished, because in all applications that we consider, the time scale for reaching the steady state configuration is extremely long, and in particular, it requires that the number of inflationary E-folds exceeds the de Sitter entropy bound. Now, this means that our applications must be in the regime of eternal inflation. On this point, I've also some new ideas, but maybe I won't present them now. And also it's been argued by Dvali and collaborators that the semi-classical approach breaks down after this time. I mean, if true, this would put eternal inflation beyond perturbative control. I think these claims are, for me, are premature, so they violate the usual effective field theory interpretation. So I suspend judgment about that. Of course, then finally, the swampland conjectures. For SOL to be realized, it is important that field excursions are super Planckian. And this is not a problem for quantum field theory, because we enter quantum gravity regime only when energy densities are super Planckian. And since the potential we consider are very shallow, super Planckian field excursions are perfectly compatible with sub-Planckian energy density. However, super Planckian excursions appear to live in the swampland, if you believe in this argument, unless you introduce non-trivial monodromy or clockwork.
Gian, there is a question by Eva.
Gian, can you explain that claim that super Planckian field excursions supposedly live in the swampland? They exist for axion fields in string theory, for example.
Right. There are exceptions, as I was saying. One can construct cases like non-trivial monodromy where you can avoid them. So I'm not, again, since I'm actually using super Planckian excursions, I'm happy if you don't have a problem. Some people just are reluctant to accept the possibility. But I agree with you that it's not necessarily in contradiction with strings theory. Okay, so okay, so actually many of these problems are not only characteristic of SOL, but are general of any framework of eternal inflation. So depending on the authors, on the people, some people may like it and some people may object it more. Okay, so now I gave you this overview of the open questions to be clear about the limitations of my results. But now let's accept this hypothesis that I can give a probabilistic interpretation of the FPV equation and allow me to proceed. So to solve the FPV equation, we need to specify the potential of the field phi. And this is the model-dependent part of the construction. However, we can use a useful parameterization that describes a class of theories, which we call EFT potential. So the EFT potential is made of two terms. The first is a constant term that describes the bulk of the energy density, and therefore, let's say, the primary driver of inflation. While the second term is a modulation of the energy density due to the field phi. And I will call this field phi the aperon. It is so it is described by two parameters as part of the potential. The typical field excursion, which I will call it F, and an overall coupling G of epsilon. So the potential is protected by a shift symmetry of phi, broken only by the small parameter G of epsilon. You can think of the aperon as for instance, as a pseudo-Goldstone boson, of asymmetry explicitly broken by this parameter g of epsilon, or you could think of it as a modulus of a supersymmetric hidden sector. But all these microscopic details won't matter for my discussion. And this function omega that you see is a generic function of order 1, which is, I assume, it's power expandable around a generic point, which with a coordinate shift, I can always call it 0, the origin. Now, because of the linearity of the FPV equation, it's useful to expand its solutions in stationary states, very much like what you do for the Schrödinger equation. So lambda are the eigenvalues that describe the time dependence. So lambda are the analog of the energy levels in the case of Schrödinger equation. And the small p are the time independent eigenmodes that satisfy this equation. So here, the parameter, all you have to know is these 2 parameters, alpha and beta. The parameter alpha measures the inverse of the Aperon coupling, and beta, the field range in Planckian units. Okay, they've been chosen in such a way that alpha measures the strength of the quantum term relative to the classical term, and beta measures the strength of the volume term relative to the classical term. Okay, so these parameters alpha and beta are sufficient to parameterize the full stochastic dynamics, of course, within my assumptions and within this class of theories, which is described by these EFT potentials. So the behavior of the FPV solution can be classified in the space alpha and beta. So for very small alpha, the Aperon coupling constant gets stronger, and eventually the approximation of treating the Aperon potential as a small perturbation breaks down. Okay, for small alpha and beta, the slow roll parameter epsilon becomes larger than 1, and so we are no longer in the slow roll regime. When beta is smaller than 1, volume effects, since beta measures the volume effect, becomes negligible, and therefore FPV behaves almost like a regular Fokker-Planck equation, up to an overall time dependent, but almost a field independent factor. And since volume effects are crucial for Sol, we are not interested in this region beta smaller than 1, which corresponds to sub-Planckian field excursion. Then the region Q is where alpha is so large that quantum effects fully dominates the dynamics. This means that quantum diffusion randomizes any distribution and erases any structure, making to a first approximation any configuration equally probable. So I cannot derive any prediction there. So this is not interesting for us. There are 3 regions which, however, are interesting for the dynamics that I'm considering. And these are the region C, which is the classical region, where the distribution mainly follows the classical equation of motion. And the field prefers to evolve towards minima of the potential. In the QV region, there is an interplay of different effects. So the field phi naturally evolves along the classical equation of motion. However, because of quantum effects, there is a tail of there is a spread and a tail of the distribution where the field is at a higher point of the potential. And those configuration has a faster expansion rate, and therefore the volume of the corresponding patch grows much more than the surrounding space. As a result, when steady state is reached, the phi distribution is peaked around a field value, which is closer to the top of the potential, the more quantum the dynamic is. It's sort of at an intermediate level, but the more quantum, the more it grows, it climbs the potential. And the width of the distribution has a universal value. You can find out that it's of Planckian size, which is independent of the interaction. I really apologize for this problem. I don't know what's going on. It gets blocked. If anyone has a suggestion of what am I doing wrong, your screen, yes, change. Okay, boom. Okay, now you see it, right? And then finally, we enter what we call the Qsquare V regime, where quantum diffusion becomes so strong that the peak of the distribution is entirely pushed towards the top of the potential. And the width of the distribution grows the more quantum the system is. So these behaviors can be seen explicitly in the case of the simple case of an exactly linear potential, because this can be solved exactly analytically. And in this plot, I'm showing you the case of a monotonically increasing potential in the field range between -1 and 1, where the field is expressed in units of f. As you can see, the asymptotic steady-state distribution of the field phi is different in the 3 regime, is localized towards the bottom of the potential in the C regime, floats somewhere towards the top in the QV regime, and reaches the top in the Qsquare V regime. And as I said, these are asymptotic distribution whose phi functional form becomes independent of time at sufficiently late times. You can think of them as a sort of thermal equilibrium that is reached after relaxation time. Actually, the analogy is rather pertinent, because thermal equilibrium doesn't mean that the system is static. Right? On the contrary, atoms move all the time, and the microscopic configuration change. However, some macroscopic properties remain static in a statistical sense. And these are the thermodynamic quantities, such as temperature. And the same for the multiverse. So each configuration of the field phi keeps on evolving as a result of the classical force and the quantum diffusion. In other words, each Langevin trajectory keeps on going, which is with its random walk, just like a single atom. And indeed, the Hubble rate plays exactly the role of a temperature if you interpret it as a Gibbons-Hawking temperature in the system. However, when you look at the multiverse as a whole, we see that the macroscopic field distribution statistically reaches an equilibrium state with some global quantities that remain invariant, just like the thermodynamic properties. And the existence of this steady state configuration, or if you wish, equilibrium states, is the reason why we dare to make a probabilistic interpretation. As a byproduct of this is that the result based on steady state configurations are independent of the initial conditions of the universe, just like equilibrium properties of the gas are independent of the initial condition of the gas. However, our results depend on boundary conditions. And these are the conditions that you have to impose at the boundaries of the field range in order to solve the FPV equation, which is a second order partial differential equation. So physically, this corresponds to the matching condition of your effective theory in the far UV. So this is information beyond the EFT control. This means that our result can be sensitive to the UV completion of the EFT. Now, depending on your taste, this could be seen as a drawback, because you need to give some input, some assumptions to your calculation about the UV completion, or a virtue, because in a future one could learn something which goes even beyond the EFT. Okay, now I gave you the enough tools to attack the physical problem. So let me try to give some example of physical problem. The first one is near criticality of the Higgs self-coupling. I'm sure that you know that one of surprise of the measurement of the Higgs mass was to find that the standard model, if extrapolated to a very large field, shows Higgs field, shows a non-trivial vacuum structure with our usual electroweak vacuum being metastable, just at the edge of a critical behavior. Now, let's suppose that the standard model coupling constant, all of them are not constant, but depend on for simplicity, just to make one scalar field, which is subject to large fluctuations during inflation. So this scalar field is the aperon that I was considering, the field phi. The scalar potential of the theory is given by two terms. The first term is the shallow aperon potential, where M is the energy cutoff of my effective field theory, and G star is a generic coupling of order 1, just to fit dimensions. The second term is the Higgs potential, where the quartic coupling lambda is now a function of phi. So for simplicity, I take the Higgs valve fixed to its physical value of 246 GeV. I always have the freedom to choose the quartic coupling renormalized at the cutoff scale as just proportional to phi, field redefinition. Of course, the renormalization group effect will make the dependence more complicated. See, now all standard model coupling constants generically are functions of the field phi as well. So let's now take a pictorial look of the effective phi potential. So as long as phi is sufficiently small, the Higgs potential is minimized at the electroweak vacuum, and the phi potential grows with phi. This is my assumption of the potential. And this is what I call here the IR phase. However, once you cross a critical value, the quartic starts becoming negative at large field. Now, the Higgs potential develops a second minimum near the UV cutoff, and the Higgs undergoes a phase transition. This gives a back reaction, like in the example that I was showing before, a back reaction to the phi potential with an additional contribution, which can change its first derivative. And this is what I call the UV phase. There is a small field region where the two phases can coexist. And so this IR supercooled branch terminates when the IR phase becomes unstable under, for instance, Hawking-Moss instantons. So if you solve the FPV equation by taking the aperon potential in the Qsquare V regime, so you have to make an assumption on the kind of potential for the field phi, you find that the steady state solution has a sharp peak localized near the point where the IR phase collapses. This can be intuitively understood from the behavior of the simple linear potential that I was showing before, okay? That sort of the field tends to climb. And the conclusion is that the critical point where coexistence between the IR and the UV phases terminate becomes an attractor for the field phi during inflation. This is what SOL is all about. The distribution becomes dynamically localized at a critical point. So,
just to ask, I was like,
please, was asking a question or what's happening?
Oh no, sorry, I think you might be addressing it here. That's fine.
Okay, sure. Okay. So my point is that at the end of inflation, there is a strong probabilistic preference for patches of the universe where the Higgs self-coupling is near critical value. Now, the actual calculation now shows that there's a region of values where for the cutoff M and the Hubble rate H0 showing in the figure, yes, where the prediction for SOL is consistent with observation. Of course, the SOL prediction refers to the end of inflation. So a question is, what happens to the SOL prediction during the thermal phase of the universe after inflation? So after inflation, the aperon finds itself at a point which is not the minimum of the potential. therefore, after reheating, the apeiron will start sliding down the potential, slow rolling in search of a minimum. And the most dangerous consequence of this late time motion is that the vacuum energy becomes time dependent. And astronomical observation give a constraint on the parameters of the EFT potential. And so in particular, they imply that this product alpha square B has to be very large. And this is why we need to be in the Qsquare V regime, as I said, and therefore, and also in eternal inflation.
Yeah, I cover a couple of questions, but maybe I know. Do Robert, do you still have a question?
Oh yeah, sorry. Just to re-ask. So my memory from previous papers looking at the Higgs true vacuum stuff is that for some circumstances, if any sort of causal patch in our past light cone was in the true vacuum, then that region would expand and sort of eat these.
Right.
So in this,
that's exactly taken into account, right? This is taken into account by so when I was showing you that potential phi, let me see this figure. Okay, this potential phi is done by integrating out, if you wish, they more than integrating out, by placing the Higgs in its vacuum configuration, and that's why you have this non-trivial structure. Okay, so indeed you're right. The difference, however, is that now I'm introducing a phi field, so that lambda, the coupling lambda, is phi dependent. And so when you change vacuum, there is a back reaction of the Higgs. The Higgs gets a VAV, which is enormous, can contribute to the energy, but because of the contribution, it contributes to the phi potential and makes the potential go down. And that's why you create this cusp, which is the signal of the critical behavior of the phase transition, and also the reason why we claim that you cannot be attracted during that point.
I maybe didn't quite ask the question correctly. So you are calculating the probability for the phi phi sort of anything, but we're sampling sort of many patches of reheating. Can we calculate the probability that any of the things in our past light cone were in the went into true vacuum, or am I misunderstanding?
So what I'm looking is I'm averaging over patches. I'm taking the Hubble constant for the moment constant. First time that the Hubble constant is constant. So I'm taking it constant, and I'm looking now as a distribution of the field phi's, and I'm solving the FPV in the setup to see what is the probability distribution of that. In the case the Higgs can contributes to this, but as a static field. Okay, this is the exercise.
Gian, I also, there's Michael, but then I also had a couple of questions on this. So first, what could you go to the previous slide? Yes, what determines this phi star? Because the IR phase is unstable, like everywhere between phi and phi plus, right? It's just the transition rate changes.
Very good question. I was a little bit quick because of time here. I should specify. This is this phi star is the point at which transitions are fast enough. Okay, so you can, for instance, I mean, the way that we estimate it is by looking at the Hawking-Moss instantons and then see when these transitions are fast enough. And that defines the field phi. This is, so in this way, I can then reproduce this figure that I was showing you before. So this is to make an exact prediction of M and H naught. This is, however, is a model dependence. Okay, so for instance, this plot here that I'm showing is very much model dependent because it depends on the structure on Hubble and so on. But in general, there will be a point in which the transition is fast enough. So you have this super cooled phase, but then at a certain point, you're going to jump down. And now the calculation of the exact point is, of course, model dependent. We've done it in a way in order to make contact then with parameters, but you expect to be there. Does that answer?
Yeah, well, I mean, I have some, but another question I had is, so here it's only lambda, only Higgs quartic that depends on phi, or the mass also depends
everything. What I'm here, well, everything, sorry. It's here I'm taking all standard model couplings to be phi dependent. You say, okay, but where is the phi dependent? The point is that the advantage of this is that at the end of the calculation, all this phi dependence of the coupling constant enters only in two places. One is lambda, okay? And the other one is beta lambda. So the functional dependence of beta, of course, beta, which is the beta function of the coupling lambda. Beta in general is a function of all the coupling constant of your theory. But now I'm treating essentially beta as a free parameters, okay? I'm only making the assumption that at a certain point, when I go to value of phi larger and larger, so that lambda is sufficiently negative, you have a beta function which is negative.
You're saying there is no strong dependence.
So essentially, I'm embedding because I'm obtaining some qualitative result. This is not precision physics. And so all I need to know is that the beta is a function of phi, and I'm making a simple assumption.
But I guess what
which means essentially I'm covering a class of field dependence of all coupling constants. Of course, you can invent some field dependence of all coupling constant such that beta has some very special behavior that changes the picture. I'm not covering those cases. I'm trying to sort of parameterize what I call it a fairly generic case, but it belongs to a certain class.
But is there strong dependence on Higgs mass? That's what I'm trying to understand, because
the Higgs mass enters in V. Okay, so in this exercise, instead, I'm keeping, and this is a very important point. I am, in order not to mix the problems, I'm keeping V, which is the mass of the Higgs, if you wish, okay? The mass of the Higgs, I mean the bare mass of the Higgs, fixed to a very low energy value. Actually, I'm getting now to the case in which I'm going to make that value. So I am trying to factorize the problems. I mean, in general, I agree with you that everything should fluctuate, but I'm making toy models. So in this first example, I am keeping the mass of the Higgs, let's call it the bilinear of the Higgs, fixed to a small value, and I'm varying the coupling constants. In the next example, I'm going to start varying now also the Higgs mass, okay? But in this example is fixed. Now you may argue, well, how is it going to be? Well, of course, these are all model dependence questions. But the message that I want to give, I'll repeat it at the end, is really that this is a framework which shows how criticality is approached. I don't want to necessarily create a realistic model of this is the model of the universe, but I'm showing that these are features which repeated themselves. And indeed, what we observe for the Higgs is that parameters are near critical. Okay, lambda is near critical.
I understand. There is also a question by Michael.
Yes. I'm really confused here. So you've taken, this problem is intrinsically multidimensional, as you've stressed, because you have the scalar field self-coupling, but you also have the top quark Yukawa coupling, or the top quark mass. And then there's V also.
But V is fixed. I'm making this assumption.
Well, somehow you fix them all in terms of a single parameter, and you have a V, which is a function of this single quantity phi. But if you allow more degrees of freedom, what this curve that you've drawn is it's a saddle point. There's a maximum along the phi direction, but it's a minimum along the orthogonal directions, right?
Now, you are thinking about varying V. Is that what you're saying?
Actually, I'm thinking about varying the top quark mass, which is
Then
the
I'm varying that. I mean, then you're getting the picture this picture that I'm showing. Unfortunately, I didn't.
No, you don't. You go orthogonal to this plane. And when you go orthogonal to this plane, the potential goes up.
No, because as you vary, now you're absolutely correct by saying now it's a multidimensional. Okay, I'm varying. Unfortunately, I don't have the plot. It's in the paper, but so it's true that it's a multidimensional space. However, the critical line, the critical surface in this space is unique. So at the end, the prediction, I'm not predicting the value of lambda. I'm predicting a combination of all the standard model couplings. The important prediction is not that I'm telling you that the mass of the Higgs is 125, but I'm telling you that there is a critical surface in this multidimensional space, which is the critical surface that separates the two phases. In any case, there are two phases, right? One in which the Higgs is in the infrared, one in which is in the ultraviolet. It's going to be a complicated hypersurface. All I'm saying is that Sol is telling you that you are close to this surface. It's not going to tell you where on this surface is. So it's making a correlated prediction of the Higgs mass, of the Higgs quartic, and the top mass, and all that, which is one plot that I don't have. So
yeah. Well,
my prediction is not on lambda itself. My prediction is out of this multi-dimensional space, what you are going to be attracted to a surface. I don't know in which point of the surface, but you're going to be in your motion attracted to the surface. And this surface is a surface in which the Higgs valve is near critical.
So let me state the question again, but so if I add dimensions to this space, in general, the potential will go up if I go out of this plane into those dimensions. And when the potential goes up, then the quantum effects carry you to the higher points of the potential, which means that you're very unlikely to be on this surface at the end if you're in the quantum regime. And that's what I'm confused about.
Right. And the answer is no. This potential, making a certain assumption on the shape of the beta function, okay? But essentially, I have to say that if it's positive, I'm making a 50-50 assumption. Then what happens is that when you are in the IR phase, this potential will tend to grow as you verify. And then when you are in the other phase, there is this back reaction and you go down. You are correct that this is not a general statement. You can invent certain functional dependence of all the couplings where this is not the case. But
sorry, let me take. I need to, John. I need to moderate a little bit. I think the answer to Michael's question is that there is only one. It's important. There is only one light field considered here, and we're looking at effective potential for this one light field that fluctuates wildly during inflation. That's why it's really a one-dimensional problem at this point. You don't. Yes. No, you can integrate out other fields.
Multi-dimension in terms of couplings. I'm considering, for simplicity.
Yes, but as a function of phi, it is a single.
I'm considering only one single field, but I'm also I'm considering that all possible coupling constants may vary, and I'm embedding this information in the beta function. If you could also take, if you want, take a simpler case, you may like it or not, but take the case in which I'm saying that I'm fixing all the Yukawa couplings, the alpha S and everything, and I'm making only lambda vary. Now you may say, oh, this is too reductive. Well, it's a toy model, but it's interesting that in this toy model, then you are really driven to the critical point. I'm saying that this is more general because you could also have a variation of more couplings, but Victor is correct. I'm considering for the moment only one single field.
Okay, Eva also had a question.
Well, sorry, you might have just answered this, or you and Victor, but my question is, you have all these interacting fields in a time-dependent setting. Does the formalism take into account all of the non-adiabatic effects that enter in that circumstance. In particular, some forms of criticality bring in new light fields. And in that context, they get produced time dependently. So basically I'm asking, do you have all the non-adiabatic effects included in this analysis?
Sorry, what effects are you thinking of?
Particle production type effects, non-adiabatic.
No. I mean, I'm really treating the field as a classical evolution.
I mean, you have classical stochastic, right? But still,
Yes.
so a little bit of quantum, but not the full quantum.
Yes, exactly. Yes.
Yeah,
I
okay,
mean,
okay.
exactly. It's as I was showing, the quantum effects gives us the stochasticity. Can you say in English? I don't know. Of the evolution, but in principle, you could have particle production from the change in background. I'm assuming that these are small effects that do not change the energetic. If you would have a strong particle production, you could. Now, I didn't look at this into detail. I suspect that the particle production is small because these, my phi field is very shallow. So the variation of the field phi is a very small change in energy. So the non-adiabatic effects of particle production, I suspect, but I didn't do any calculation, I suspect in this setup should be small. But it's a good question, okay? May I continue?
Yeah, there is also Andre.
Okay, please. The slides, by the way, got stuck. I think they get stuck after a while if I wait too long.
Okay, can I comment?
Yes, we hear you.
Okay, well, I have actually in the same direction, like Mike Peskin, maybe a little bit even further. When we study such distributions of different results of the experiment, one of these issues is, for example, the present temperature of the microwave ground radiation, which could seem to be irrelevant to all of this discussion, but in fact, it's very relevant. Because when this set of measures was studied a long time ago, like 20 years ago, it looked like okay. But then Max Tegmark and others, they found this Youngness problem, which was discussed. And one of the manifestation of the Youngness problem is the fact that for all measures of the type considered here, with exception of extremely small value of parameter psi, which was not considered here, for all of these measures, there is a prediction that we cannot live right now in a state with temperature of microwave ground radiation 2.7 Kelvin. The probability of that is exponentially small. And that looks like strange things, but nevertheless, this is something which many of us who studied probability measure problem in string landscape theory, we have all studied this in detail. What Raphael Busse is here can confirm. So all of those who study right now probability measure problem in multiverse, none of them consider measures of the type considered here because they are dangerous for other predictions, not for prediction for the Higgs field, for whatever other thing, but for trivial predictions like the temperature of the part of the universe which we observe right now.
Absolutely.
So there are several different measures which do not suffer from this problem, but these measures have not been used in this investigation.
Of course, you are completely right, and this is the point that I was alluding before. So if you apply blindly this measure to the inflaton, you run into a problem because you have Youngness paradox, and our universe is exponentially unlikely. However, the point that I want to make is that you can see that even if you apply a single measure for this setup, the measure of the inflaton is completely independent on the measure of this other field, the phi. So meaning that you can, we have one example in a paper, you can define setups in which the inflaton does not have a steady state in proper time with xi equal to 1, but the field phi does. So all I'm saying is I'm taking this as a simple example, waiting for a final resolution of the measure problem. Once we'll have a final resolution, one could apply to that case. But I'm trying to make it again. My attitude is more of a toy model, trying to play with these ideas, because this is a simplest example that one can work with, and then see what the results are. Will these results about the fact that criticality becomes attractive, will they survive if you start changing the definition of the measure? I don't know the final answer. Okay, one could try to work out other examples. It could be interesting to do it. It's an exercise that is in our list of things to do. Somehow I have some intuition that some of these properties are robust and may remain in certain classes of measures. The problem is the difficulty of approaching that is that we don't have a good final example of what is the right measure to use. I mean, if we did, I think we would really be more motivated to attack that. Please, there's another question.
Raphael?
Excuse me, may I reply for that? My main point was that it does not depend on our desire to which fields we apply and we do not apply the measure, because the measure is essentially slicing of the universe, and then you study everything that is in this slice. So what we say that the Youngness problem, which I discussed, means that whatever results you obtain concerning the properties of elementary particle physics, there is one unique prediction of this set of measures for all these slices, if you do it slices. And that is, we cannot live in the universe with the temperature 2.7 Kelvin. We must live in the temperature where we cannot actually live. It is so hot. So that is a prediction for this set of measures. If you choose a different set of measures, you different set of slicings, then you have different predictions for all of these parameters and everything simultaneously. But you cannot choose to which it applies and which it doesn't.
I agree. Let me just one second, and then I let Raphael talk. All I'm saying is that I'm not applying different measures to different fields. I agree with you that would be very ad hoc. I'm not doing that. Okay, I'm just saying that one can actually, I'm using a measure that you were proposing at a certain point, that when you define a measure and you have certain selections on that, you see that it acts differently on different fields. And so in particular, I can give you an example in one in which you do not have the Youngness paradox, and yet the results for the distribution of phi corresponds exactly to my calculation. Now, I'm not defending that particular choice because it's not more motivated than others. But what I'm saying is that you cannot rule out these kind of phi distribution just based on the Youngness paradox. Please, Raphael.
Yeah, I guess there's a good point to follow up, actually. So that's exactly what I think Andre and I disagree about. The theory our theories, right? Ultimately, their purpose is to make predictions based on probabilities that we calculate from them. Before you pick a measure, you don't have a theory. There are no well-defined probabilities at all. So the measure is very much part of the theory. Mm-hmm. So you don't get to pick and choose different measures for different questions you want to ask. Once the measure has been ruled out based on any one question, that theory is dead by the usual rules of how our theories work. Or how we judge them, right? I think that's sort of the only bad news. And the good news is something Andre said at the beginning, there are actually measures that have not been ruled out based on these catastrophic predictions. And so it would be really interesting to study what such measures tell you for the kinds of questions that you are asking. But I think using a measure that's already been ruled out it's like saying, let's see if the, I don't know, steady state model of the universe predicts something interesting when we ask the following question. Well, no, we don't, because it's already been ruled out, right?
Right, but point well taken, and I agree with you that we should explore other measures. But I'm saying that you can define some measures, globally, not for us, the different fields in a different way, which give you that for the inflaton, you get a prediction which is, for instance, the one of psi equal to 0. Okay, while for other fields is not. So that particular choice is not ruled out by the Youngness paradox. Okay, so what I'm saying is that the example that I'm giving corresponds to a single choice of measure for all fields, which is not inconsistent with the Youngness paradox. Now you can ask, was that a good choice? Maybe not. Maybe that's not the best choice, but it's not inconsistent. It's not ruled out. Okay. What is the level of your patience?
Well, we're usually relatively flexible on the. Yeah, you don't like. We don't have to. If you have, look, people are free to leave, even those people who are here in person. But maybe we can give you a round of applause, no, at this point, okay. And then if you want to mention some other things, you can just
maybe one. Yeah, I know. Am I sharing or not?
No, you stopped sharing. Okay, let's thank Gian for.
Okay.
We talked that he got to like a third
so
of his life.
If you want the few survivors, I can tell you.
Gian, I have one question. I'm sorry.
Please.
While you're setting this up, so you said at the very beginning that the distributions you get, their central value is gauge independent prediction, but their distribution is gauge dependent. I'm still very confused by this statement. So what is the sort of what is the sharp theoretical prediction that is a gauge independent thing? I don't know what it means when you tell me that the distributions.
The sharp prediction is that in this setup, that when you solve the FPV equation, you'll find under certain assumptions, so you have to be in the Qsquare V and blah, blah. You make certain assumptions, and then you find that your distribution is peaked at the critical point. Okay, that does not depend on psi. When I say is gauge independent, I'm just making the calculation with this parameter psi, and I'm seeing that the location of the maximum does not depend on psi. However, the width of the distribution is psi dependent. And if you go, unsurprisingly, if you go to psi equal to 0, this distribution gets infinitely large, and so you lose any localization. So you lose the localization when you get to psi equal to 0, which is E-folding gauge, because then there's no field dependence, so obviously the distribution is flat in the field. Okay, but so since phi is a parameter that interpolates between proper time and E-folding gauge, it's not surprising that you go to the case in which you have a very sharp peak to the case in which you have no peak at all, and anything in between is just this distribution got broader and broader. But the fact that you are at the critical point remains independent of psi. Of course, if you set psi equal to 0, since now this distribution has become infinitely large, now you lose also the information about where the peak is. Okay, it's completely flat. But psi equal to 0 is in a sense is a pathological point for our purposes, because you lose any phi dependence.
So sorry, I'm confused then by what this Xi parameter really is. Is this like I thought that this was just a gauge choice of what you're calling your time coordinate, but there is a natural gauge. Like I would want to pick the gauge that I match onto today, right?
Well, I mean, there could be yes, there could be a right, let's call it a correct foliation, which is a one, for instance, that corresponds to the reheating surface. But simply, I don't know which one it is. And that's why I'm doing this foliation, and I'm changing the foliation by changing this parameter xi. It obviously is not an exact result, but there's no way that you can predict you can tell which is the correct foliation. The only one that I can imagine is a one which is synchronous to the reheating surface.
Good. So in that sense, it's really a family of measures, right? You're saying it's really corresponds to a family of measures, right. You know, and you're saying that you can calculate, you know, to Raphael and Andre's question, you can pick some value of C that for which this family of measures does not.
Right. And in all exactly, and in all the examples that I'm making, there will be 3 examples. I made one. The value of psi plays very little role unless you go really psi equal to 0, because the parameters are such, all the other parameters that enter the game, once you are in the right conditions, that these distributions are actually extremely sharply peaked. So, you know, if you change this parameter xi by a couple of orders of magnitude, it's not the qualitative thing is not going to change. Okay, this is why I'm trying to argue that this result, in spite of the limitation of the calculation that I'm not trying to hide, somehow it may be, it may correspond to something physical.
Thank you.
Now, Victor, may I ask you honestly, what shall I do at this stage? So,
well, I think if you have some, don't try to go through all your slides probably at this point, but if you have
let me
some,
try to do it in 5 minutes.
Sure. Well, if you think you can do it in 5 minutes, sure. But otherwise, you can just.
I'll try to give you, just give you an idea. Okay. So let me try to. Now, I am sharing or I'm not sharing? Yes, I am sharing.
Well, it's a little bit weird. Well, you're sharing, but it's not full screen. Yes,
I'm coming to that. I have to do full screen. Okay.
By the way, one thing you didn't try was just to try slideshow. No, I don't know. Maybe slideshow.
Now you see it because I'm doing it. But anyway, let me just really 5 minutes because I agree with you. So I can apply these ideas to the case of Higgs naturalness, because also there it is, I claim that Higgs naturalness is a problem of criticality. Criticality now means that Y is the standard model in terms of the Higgs mass parameter. Y is just at the verge between broken and unbroken phase. And you can play a similar game, and you can let the parameters vary, and you can see that it may work. However, you get a hierarchy from this, but in order to make the result realistic, you have to add some additional matter. So the conclusion is that yes, it can work, but you need to add some model dependence. Then last example is the case of the cosmological constant. I believe that this is interesting conceptually because it's quite different, and the game here is played by 2 different phases. I have one phase which is supersymmetric and asymmetric. So because of that, the vacuum energy is exactly 0, okay? Because the superpotential has to be 0 by R symmetry, and the auxiliary fields have to be 0 by supersymmetry. And then I have another phase which doesn't know anything about supersymmetry. So in general, you may say, well, okay, the system is completely decoupled. But then if I introduce some transitions between the 2 phases, and then a field phi that scans the parameters so that you can have coexistence of these 2 phases, what I find is that the distribution is peaked at the point where the two phases are degenerate in energy. Okay. So this is, I find is very peculiar, right? Because why is let me see if I can right. I mean, maybe with this you can see. Now so why does the system choose to be degenerate? So a vacuum that doesn't know anything about supersymmetry prefers to be at a point which is almost exactly degenerate with another vacuum in which supersymmetry and R-symmetry guarantees that the cosmological constant is zero. And the secret of this result really lies in the macroscopic behavior of the system. A single Langevin trajectory doesn't see anything special in this critical point. It's exactly like when you put two boxes of gases together, any single atom doesn't see anything special in a particular value of energy. And yet, when you put them in thermal contact, the two boxes of gas equilibrate themselves to reach the same temperature. Well, in the same way, in the steady state configurations, the two distribution reach a configuration in which, even if each trajectory doesn't know anything about the trajectory in the other vacuum, they equilibrate to reach degeneracy in energy. And this gives the explanation for the cosmological constant. I think I should stop at this point, okay? Thank you very much.
Okay, yeah, thanks. Let's thank Gian again for that. And I mean, yeah, if we have